见了，不见了。刚刚那个，他是做错了，是吧？
他是第二，
刚刚那个，
你说
对，
我不知道，
所以我说那个这没看到过，怎么会有？
对，我也没看过，
所以他是做错了，是吧？
应该是。
Okay, good morning, everyone. So it's about time to have today's seminar. Welcome to the last seminar of this semester. If I'm not mistaken, today we have 5 presenters in total. So I think we invite 2 questions for each presenter. Okay, and then I think the first presenter will be. So you may start when you are ready.
Good morning, everyone. My name is Li Hongzhou, and my advisor is Ye Zha. And today I'm going to present our work title, Two-Stage Transformer Postnet for Minimal Radar 3D Human Pulse Estimation. This work focuses on estimating human 3D skeletons using minimal radar signals. The main idea is to directly learn human pulse from radar range documents, while avoiding heavy preprocessing such as point cloud extraction or CFAR detection. Here is the outline of my presentation. First, I will introduce the background and the motivation of radar-based human pulse estimation. Second, I will explain the proposed 2STR pulse method. Third, I will show the experimental results, including quantitative comparison, visualization, and ablation studies. Finally, I will conclude the presentation and discuss possible future work. Let me start with the introduction. Human pulse estimation, or HPE, aims to estimate human key points and represent body posture. It is important in many applications. For example, it can be used in human-computer interaction, healthcare monitoring, smart environments, and security systems. It has been widely studied in computer vision. As shown in the examples, human key points can be used to describe body posture. However, camera-based systems have several limitations. They are sensitive to lighting conditions. They can be affected by occlusion, and they also raise privacy concerns because they capture visual appearance. These limitations motivate us to explore radar-based human pulse estimation. In this work, we focus on a different sensing modality, millimeter wave radar. The goal is to estimate 3D human pulse from radar signals in a privacy-preserving way. Compared with RGB cameras, mmWave radar has several advantages. First, radar is more privacy-preserving because it does not capture visually identifiable human appearance. Second, radar can work in darkness and poor lighting conditions. Third, it is more robust to partial occlusion because it senses radio reflections instead of visible images. Therefore, mmWave radar is suitable for indoor healthcare, smart home monitoring, and other privacy-sensitive applications. However, radar data are very different from images, so the key challenge is how to extract useful pulse information from radar signals. The research problem in this work is to estimate 3D human pulse directly from primal radar sequences. The input is a sequence of radar range Doppler maps, and the output is the 3D coordinates of 24 human joints. The key question is whether accurate 3D pulse can be learned without point cloud extraction or CFAR detection. There are several challenges. Radar reflections from the human body are indirect. Some distal joints, such as wrists and ankles, may generate weak reflections. The radar signal also contains noise and sparse motion cues. In addition, it is difficult to preserve temporal consistency across frames. previous radar-based HPE methods rely on heavy preprocessing. For example, some methods apply CFAR detection, target list extraction, point cloud construction, or angle result radar tensor generation. These preprocessing steps can be useful, but they also have drawbacks. They may remove useful reflections from small body parts, such as wrists or ankles. They also require manually tuned parameters, which may not generalize well across different environments or sensor settings. In contrast, our method directly uses 3D range Doppler maps. This keeps the pipeline simple and allows the neural network to learn useful radar features end-to-end. Next, I will introduce the proposed method. The proposed framework is called 2STR pose, which stands for two-stage transformer pose net. The core idea is to use minimally processed radar data and a two-stage transformer decoder to progressively estimate human 3D pose. This slide shows the overall workflow, starting from the raw MIMO radar frame sequence. We first apply three basic processing steps. Range FFT stands for fast Fourier transform, static cluster removal, and Doppler FFT. After that, the resulting range Doppler maps are fed into the proposed 2STR pose model. Finally, the model outputs the 3D human skeleton. The important point is that we avoid CFAR detection and point cloud extraction. Instead, we directly use minimally processed range Doppler maps and let the neural network learn pose-related features. Here's a closer look at the radar input and pre-processing. The raw MIMO radar data are processed by range FFT, static cluster removal, Doppler FFT, and complex to real value conversion. The final input is a real value range Doppler feature map sequence. This preprocessing is lightweight. It preserves more radar measurements structure compared with sparse target lists, while still removing static cluster and extracting Doppler information. This design is important because Doppler information helps capture human motion, while avoiding unnecessary detection-based information loss. This slide shows the overall architecture of 2STR pose. The model consists of three major parts. The first part is the range Doppler spatial encoder, which extracts per frame radar features. The second part is the temporal aggregation module, which uses long-term memory to summarize motion information across frames. The third part is the two-stage transformer decoder, which first performs spatial grounding and then refines the pose using temporal context. The spatial encoder extracts per frame features from a range Doppler map. It contains CNN block, stands for convolution neural network blocks, and multi-path self-attention blocks. The CNN blocks capture local range Doppler patterns, such as local reflection structures. The MHSN blocks capture long-range global interactions among radar focus. This is useful because human pose is not only determined by local reflections, but also by the global relationship between body parts. Therefore, the spatial encoder provides a stronger feature representation for the following encoder. After extracting spatial features from each frame, we use the temporal module to summarize motion information. First, the spatial tokens from each frame are pooled. Then the LSTM generates a spatial temporal memory. Finally, the fusion encoder combines the current spatial feature with this temporal memory. This module helps the model understand motion across frames, instead of estimating pose from only one radar frame. As a result, the predicted skeleton can become more temporally consistent and more stable. The two-stage transformer decoder is the core design of 2STR pose. In the first stage, the spatial decoder uses learnable joint queries to attend to spatial radar focus. This produces initial joint-wise spatial grounding. In the second stage, the fusion decoder refines these joint tokens using spatial temporal memory. This improves temporal consistency and motion plausibility. In other words, the first decoder gives an initial post estimation, and the second decoder refines it using temporal context. After introducing each module, this slide summarizes how the overall architecture is trained and used during inference. During training, both decoder stages are supervised. The spatial decoder produces an intermediate prediction, including the joint offsets and the body center. The fusion decoder then produces the final prediction after incorporating the spatial temporal information. For the loss function, it applies supervision to both stages. This means the model learns not only final post prediction, but also the intermediate spatial representation. This helps the spatial decoder provide better joint-wise grounding before temporal refinement. However, during inference, we only use the fusion state prediction. The final 3D human key points are obtained by adding a predicted joint offset to the predicted body center. So in summary, the spatial stage output is mainly used to guide training, while the fusion stage output is used at the final post-estimation results. Now I will move to experimental results. I will first show the quantitative comparison with previous methods. The evaluation metric, MPJPE, stands for mean per joint position error. It measures the advantage euclidean distance between the predicted 3D joint positions and the ground-truth 3D joint positions. Therefore, a lower MPJPE means better post-estimation accuracy. This table compares QSPR post with previous radar-based human post-estimation methods. On the red post benchmark, QSPR post achieves the best average MPJPE. Compared with PNP post AT, which uses 2D target lists, our method improves the MPJPE a lot. Compared with ray proposer, which uses 4D range Doppler angle maps, our method also achieves a lower error. This result shows that direct learning from 3D range Doppler maps can be effective for radar-based 3D human post estimation. More importantly, our method achieves this without CFAR detection or point cloud instruction. This slide shows visualization of low and high error cases. The blue skeleton is the ground truth, and the orange skeleton is the prediction. In the low error cases, the predicted skeleton closely matches the ground truth. This indicates that the model can successfully recover the overall 3D body structure from range performance. In the high error cases, the coarse body structure is still preserved, but larger deviations appear in difficult poses. In particular, the main error can come from body position or from ambiguous link reflections. This suggests that the model already captures the global pose structure, but there is still room to improve robustness for difficult body configurations. This slide studies which radar preprocessing steps are necessary. We convert 5 settings: raw radar data, removing SCR, removing Doppler FFT, adding angle FFT, and the default preprocessing module. The raw data setting diverges, which means that directly using raw radar data is too difficult for stable training. Without SCR, the MPJP increases, showing that static cluster removal is important. Without Doppler FFT, the MPJP also increases, which shows that Doppler information is also useful for motion-related post estimation. Adding angle FFT increases the computational cost, but also the accuracy is still worse than the default modeling. Therefore, our default preprocessing, which uses range FFT, SCR, and Doppler FFT, gives the best results. This slide shows 2 ablation studies. On the left, we study the effects of input sequence length, and as the sequence length increases, the MPJP decreases. However, after n equals to 10, the improvement becomes smaller, while the computational cost continues to increase. Therefore, We've chosen n equals to 10 as the default settings because it provides a good balance between accuracy and computation. On the right, we study a model component. Removing MHSA increases the FTP. Using only a one-stage decoder increases too. Removing a body center prediction also increases. The full model achieved the best results. This confirms that MHSA, two-stage decoding, and center offset prediction all contributes to the final performance. Next, I will summarize the main findings of this work. In this work, we presented two STR codes, a direct range doctor-to-post framework for MIMO-radar 3D human pulse estimation. There are three main findings. First, CFAR and point cloud extraction are not necessary for accurate radar-based human pulse estimation. Second, two-stage transformer decoding improves spatial grounding and temporal refinement. Third, the proposed model achieves 5.86 cm FTP on a red pulse benchmark. For future work, we will focus on improving distal joint accuracy, especially for wrists and ankles, and evaluating the model in more challenging real-world scenarios. And these are the main references used in this presentation. Thank you for your attention.
Okay, thank you.
Wrists and ankles are distal joints, and their radar reflections are often weaker and more ambiguous than the torso or larger body pulse. They may also move faster and be more easily affected by sparse reflections. So that is why errors are often larger for difficult pulses involving this.
Okay, since we have quite a lot presented today, so we open for another question. Any other questions? Okay. Thank you for your quite comprehensive presentation regarding your research work. And then, if I'm mistaken, in your one as well, the limitation of eliciting technique, then you provide the summary, right? Then may I know in that table, the summary, the other research group they choose the 2D and the 3D. No, this one. Oh, maybe that is one. Oh, so it's a 2D and 2D, 3D, and 4D maps. So may I know what is this 4D map? What are the parameters or variables to be considered or included?
For the 4D maps, so the MIMO radar capture the information to like the MIMO radar consists of RX, receive antenna and transmit antenna.
Oh,
And it is construct a 2D virtual antenna. And we have fast time, slow time.
This time, slow time?
Yes, so there's the 4D maps.
Okay,
So do pre-processing steps, they can get a 4D maps.
Okay, thank you. Yeah, thank you for your presentation. So we invite the next one, the second presenter, Ding Shengquan.
serial data transmission and integrated sensing and communication. Achieving such an intensive airflow coverage within a single ship is critical for modern eye farming to support multi-standard operation and diverse mission requirements. Therefore, power amplifier must be used to boost the output power of the signal and ensure the signal quality during transmission. PA needs to be operated for wideband frequency. The linearity of a PA is also crucial characteristic in the circuit design. As poor linearity leads to signal distortion, affecting communication quality. The proposed PA used gallium nitride process, achieving excellent performance, particularly in high frequency. The electron mobility of gallium nitride material is higher than the traditional silicon material, which gives gallium nitride PA a great advantage in high frequency application and can provide higher operation frequency and better performance. Additionally, it has high efficiency, which is important for lower power consumption and reduced heat generation. PA based on the gallium nitride process are capable of handling higher power outputs, which is a critical requirement in wireless base station, radar, and microwave communication. This is my visual slide. Distributed amplifier provides exceptionally fast operation bandwidth by utilizing optical transmission line to absorb device parasitic capacitance. Nevertheless, their gain only increase linearly with the number of stages, leading to poor gain efficiency and faulty chip bookings. In terms of balance architecture, they offer several wideband matching characteristics, but require 90 degrees coupler yet occupy substantial layout area and introduce interesting insertion loss, which diminish the saturated output power. Circuit design. This page shows the proposed circuit architecture. There are three key technical points. First, we utilize the 0.15 micrometer gallium nitride EMOS process and implement a two-stage cascaded design, which consists of a driver stage and a power stage. Second, we design semantic matching network for the interstage and power stage output. Here is the key to observing device parasitic capacitance, which allows us to achieve an ultra-wideband from 6 to 18 GHz. Third, active adapting biasing. The network enables single 5 volts supply operation without needing another voltage source. It can compensate for gate leakage curves, preventing bias drop and significantly enhancing large signal stability. This is the equivalent T network. Conventionally, wideband matching networks are directly implemented using transformer. However, tuning a transformer through EM simulation is tedious and time consumption. Therefore, to achieve best design tuning, we mathematically derive the transformer model into the equivalent T network. With this equivalent model, we can see directly from the bandwidth formula. Here. On the right, that the observed bandwidth is mainly determined by the center frequency omega 0 and the coupling coefficient K. This means we can precisely and quickly control the bandwidth simply by shifting the mutual inductance N to adjust K. Completely eliminate the need for tedious transformer EM tuning. This two-stage PA was designed with cascade operation to get more linearity, gain and conversion efficiency, but less power consumption. Therefore, the VGS is selected to be 0.5 volts and VDD is selected to be 5 volts. 75 micrometer for the first stage and 100 micrometer for the second stage. We also integrated the stabilizing receptor to ensure robust overall stability. This page presents of full schematic. It shows the overall architecture. We include the input and output measuring network for both the first and second stage. It also integrates our adaptive biasing circuit and DC bypass network to ensure robust stability. This is the driver information network. The circuit is composed of a DC block, a shunt capacitor, and a series inductor. It is then followed by a shunt inductor connected to the biasing network to complete the including matrix. This is the driver input bypass. The interstage matching network, it connects stage 1 and stage 2, ensuring maximum power transfer and optimal matching across the 6 to 18 GHz band. Bypass function is to filter our bias line noise and ensure DC supply stability, preventing low frequency of oscillation under non-signal operation. The power output matching network. The signal from the power stage passes through the series conductor with a strong inductor tied to the 5 volts biasing network additional. It then propagates through another series inductor, a shunt capacitor, and finally a DC block to reach the output head. The power output bypass. Okay, so for conventional specifications, we want to avoid bias supplies. So we design an active bias circuit to run the whole system on a single 5 volt rail. By carefully choosing the resistor and transistors, we can step down 5 volts to 0.5 volts. Since this circuit biases the base terminal, it is designed to draw very little current. Moreover, because 35 device typically suffer from leakage, incorporating the active bias circuit also helps suppress and compensate for the leakage current. As you can see from the figure, the current from the constant supply is in the milliamps range. However, with our active bias circuit, the gate current is significantly reduced to the microamp level. This is my chip board with a core area of 1.15 square millimeters. To achieve single supply operation, both EG and VDD are set to the 5 volts. The circuit was measured using wafer forming and 1000 micropental capacitance with active at the bypass for stability. The measured DC current are 33 milliamps and 45 milliamps. Also, because the current closely matching our simulation once the voltage was fixed, we didn't perform further current reading to save measurement time. Measurements. This figure illustrates the comparison between simulated and measured parameters. Overall, the measurement shows excellent agreement with the simulation within our target band to 6 to 18 GHz. The in-band S21 is well above 20 dB, and both S11 and S22 remain below -10 dB.
stay on this page. May I ask like the photo on the right corner? What is it? No, page 24. What does it mean on the right bottom figure? Like what does the red and blue and pink line mean? 这三个数字是什么？
你说右边吗？
右下角。
哦，red is the gain and blue is the PL. Pink is the PAE.
Okay, and move on to page 23. So why isn't the measure SQ1 flat around 60 Hz?
Okay, the main reason is that this is an ultra-wideband design covers 6 to 18 GHz. With such a wide bandwidth, the lower band edge specifically around 6 GHz is highly sensitive to the external setting environment, including proper contact and PCB boarding.
Thank you. So I would like to invite the first presenter of today, will be Yang Zhijie.
teacher has to set anything up. And this is where an object detection module comes in. But I'll talk about this in a moment. So here is the intuition behind our system. You can think of it as a simple pipeline on the left. OCR reads the answer and compare, check if they are correct, generate, create the markup instructions, and paste, put everything on the paper. But there's one thing missing. How does the system know where to put the markup? So this is the key problem. And the answer is yellow, the object detection module on the right. It was give our system a special everywhere this evening. Let me show you how it all fits together. So now let's go into the actual system. This is the full data flow of data. You can see two paths coming out of these two. The top path goes through OCR and compare. That's where we read the answer and check if they are correct. The bottom path goes through YOLO. That's where we detect where the answer boxes are on the paper. Both paths feed into generate, which take all the information and decide what markup to put where. Then path render everything onto the original image. So let's go through each part one by one. First, I will show OCR and compare. So this is what OCR and compare state look like. The input is the scan exam paper. This is teacher answer and this is student answer. So it contains both the teacher correct answer and student handwriting. And our module is Gemini Pro. Gemini Pro reads both of them at the same time and compare take those two sets of answer and check them question by question. The output is a structured JSON file. You can see it on the right. For each question, it records the standard answer, the student answer, and whether it's correct or not. It also gives us an error list and a total score. This strong output is what gets passed to the generate stage data. So the key thing here is we are not just getting a score, we're getting detailed information about every single question. And this is at the bottom test and spatial localization. So this is a yellow stage. The input is the same scan exam paper, and our module is yellow V8. Look at the image and detail. Where each answer box is give us the boundary box coordinates for every answer written on the paper. And we train you on 250 annotated exam image with some basic geometric augmentation like rotation, lead, and quote. To handle a blank that scans paper are always perfectly straight. The result was really good across our entire data set of 110 exams. There was only one box missing, so the detection is very reliable and the coordinate is output what allows the generate stage to know exactly system everything you need to produce this output. Okay, so now let's talk about the results. First, let me explain our experimental setup. Our data set has 110 research papers in total. We collect 22 exam templates from the public next exam as well as Wooling Senior High School, and then simulate 5 student response for each template, give us 110 paper total. And why simulate? Two reasons. First, we want to control the distribution of error, like 2 error, 3 error, or 8 error. And we need a specific number of wrong answers in each paper to do a fair comparison. Second, real student data is hard to get, but we are planning to work with actual school in the future. We split the 110 paper into 90 for accuracy evaluation and 20 for efficiency testing. For Euro, we trained on 250 image with some easy geometric augmentation. Our evaluation metric is grading accuracy, which is things like the ratio of correct test markup to required markup, and we compare with data. Row for E to E and row for module and our system. So here are the accuracy results. Looking at the graph, the red line is Vegas, the dark dashed line is for module, and the gray dotted line is for E to E. And the x-axis shows the number of incorrect answers in each exam. For 2 error on the left to 7 error. Overall, Vegas achieved 86.66% accuracy compared to 77.10% for manual and 60.49% for Pro E to E. That is a 9.56% improvement over the baseline. What is interesting in the trend as complexity increase, as the number of errors goes up, all 3 systems get worse. That is expected, but Vegas degrades much more gracefully at 7 or more errors. Vegas still maintains 73.33%, while Pro Mario dropped to 54, and Pro EV all the way down to 35. This shows that coding guidance doesn't just improve average accuracy, it makes a system much more robust when seeing gate conflict cases. Now let's do efficiency and cost. The dark bars are processing time and the red bars are API cost. Looking at the number, it will take 152 seconds and cost $0.0273. Pro module actually takes the longest at 184 seconds and 0.031. And Vegas only takes 93 seconds and only 0.01. That's 49% faster and 64% cheaper. And the modular baseline, how? 2 reasons. First, we replace streamline flow in the journal base stage with streamline flash, which is much cheaper per image. Second, because we provide coordinates, the module is about 77% fewer token. It doesn't need to describe where things are, it just gets the coordinate directly. So This usually comes from an OCR mystery, where the system failed to recognize the student handwriting correct. We also saw some incorrect total score, where an upstream error propagates and affects the final score. Most of these failures trace back to the early stage of the pipeline. If OCR or complaint make a mistake, everything downstream gets affected. So, what did we learn for all this? Let me break it down into 3 points. First, why does data work? The key is coordinate guidance. When you give the LM precise coordinate, it doesn't need to figure out where to put things by itself. It just makes a decision of what to do. This is important because LMs are actually not very good at ratio placement on their own. By separating the spatial problem from a decision problem, we get center accuracy and low cost at the same time. Second, our data set has limitation. All response were simulated by us. We have the test with real student handwriting because of DS. Also for calculation criteria, our simulation only has 40 correct or completely unanswered response. So we haven't really tested how the system handles partial calculation work. These are things we need to address in future work. So the bell mode, wrong position trace back to your coordinate offset, missing mark and compare error trace back to upstream. Pipeline mistake, improving OCR and compare accuracy would directly use most of this value. And now we have been working with Minhu Junior High School on the real world extension of Vegas. Instead of multiple choice criteria, we are now take open and is made criteria. The kind where students need to show their full calculation process. The data here is real. Actually, students handwrite from a real calculator, and the system uses the same coordinate guidance, but not at the same level, not just the answer box level. And here what it looks like. On the right is the teacher actual grading. You can see red bars, and you can see here some marks like this. And the left, that is our system now output. You can see red bars around each calculation step with the notation explaining what went wrong. The key thing here is our system output copy. Zero was the teacher actually wrote same procedure. Same kind of feedback, and this is the real student data, not the real data. Quantity evaluation is still in progress, but the qualitative results are already very promising. So we have 3 main takeaways. First, coordinate guides application work. Provide precise coordination layer and roll from visual reasoning to placement decision, which is why a cheap module can be an expensive one. Second, complete visual grading workflow are automated. Vegas doesn't just deploy it, they test the full markup process visual do by hand. And third, this extends to real world open-end grading, as we shown with the Minhu Junior High School project. We think this opens up a practical path toward automated grading that actually helps teacher and students, not just replace a number. Here are our references for anyone who wants to follow. And that everything concludes.
Thank you. I would like to open the floor for questions. 2 questions only. Any questions? No question. not, is it correct or not, like,
Oh.
like the bounding box.
We will do it in the future. It is not finally, I still make it. Because OCR is now very good. German Pro is enough to this case, so we don't have to do it.
Okay. Thank you.
Okay.
So let's welcome the next presenter, Chen Hongmin.
Hello everyone. My name is Hong Chen, and my report is skeletal-based human agent recognition using working watch convolution, neural network, and far neural network. And in my introduction, the research focuses on agent recognition in medical environments. Based on the exciting serial model, we add a FR model to replace the original fully connected layer. It's this way, the model makes decisions not only based on the value of each feature, but also on how different features are related when they appear together. As a result, the model can better handle feature overlay, data uncertainty, and unclear classification boundaries. And traditional agent classification methods usually use a video clip as one template sample and pick one agent label to click. And this method works well for videos with simple content and clear defined agent classes. However, in real life, human agents may change quickly over time. Different agents usually do not switch suddenly, but often have a continuous transition process. Therefore, it is difficult to clearly define when one agent ends and another agent begins. This means that the time boundary between agents is hard to label accurately. So we can define the agent label to each image based on what we want the model to learn. For example, if we think frame 1 to frame 4 belong to the same agent, we label them as agent 1. And if we think frame 5 to frame 7 belong to another agent, we label them as agent 2. So when we define the agent label for each frame, we also define a time boundary between two agents. Sliding window use a window of the same size to slide so continue video data. It cuts a long video into many
sliding windows by their agent levels, and then use them to train the model. And in traditional CL-based agent recognition models, the fully connected layer usually converts input features directly into classification results. Also, we can observe the weights of each layer. These weights are difficult to display as clear and painful rules. In our model, the later part that makes the final classification is replaced by a fairly narrow neural network. This turns the input features into degree of belonging to different Farley sets. Use Farley inference to combine the relative degrees of different features. Create rules to decrease how different feature states are related. This allows the model to make decisions not only based on the weights of the fully connected layer, but also based on the Farley states shown by the features. And my input case is now a quiz. It's connected into the degree to which it belongs to different Farley sets. We define three Farley sets: negative, 0, and positive. That's that. For an input value case, we do not directly decide that it is negative or positive. Instead, we use three Gauss functions to calculate how much x belongs N, and T. So the set of N is at negative N, like this. So when a case is close to the negative, neural case become larger. The set of D is at 0. So when a case is close to 0, newly a case becomes larger. The set of the P is at positive N. So when a case is close to the positive, newly a case becomes larger. Therefore, after qualification, one input value case will not give only one output. Instead, it will give three negative. So next, our model has four input features: x1, x2, x3, and x4. After qualification, each feature is converted into three Farley negative values. For example, there is one Farley rule. When x1 is more like negative, x2 is close to 0, x3 is more like positive, and x4 is more like negative. This rule will be activated. However, this rule is not simply true or false. It depends on how well each condition is matched. Finally, each rule differs down to each of the four classes. Because each input has three Farley sets, NVP, there are four input features. Therefore, there can be 3 to 4 powers NVP combination rules. Finally, the model combines the output of the all row with weights. And this is my model. First, the scale data information is converted into 4 input forms by using the temporal relationship between different medial frames and the distance between neighboring scaled jumps. 128 features into 32 groups. Each group has 4 inputs. Each independent F1 receives 4 feature groups. Size each feature has 3 body sets. They are 3 to 4 power possible combination. So to avoid too many outputs and making the second layer harder to track, we add a body connector layer after each branch of the first F1 layer. Is this way? We obtain 32 output. So we take the 32 output from the first F1 layer and split it into 8 groups. Each group has 4 features. Then each group goes for the second F1 layer. It's 348 output. Finally, we set the outputs into a fully connected layer to place it the action into 4 places. So this is my result. Finally, we use default detection function on our AI car. It helps me find dangerous situations in medical place. If an emergency happens, the monitor will show a warning shot. This helps prevent serious accidents. So this is my report. Thank you. And it's Q&A.
Okay. I would like to. Okay.
Window containing actions. How do you determine which category the window belongs to?
There are usually 3 methods. The first is to take the average. The second is to take the majority. And the third is to take the lesser frame of the window. The method I use is to take the majority.
How is the window size given? Or can it be any size?
Okay. There is no limit to the window size, but if the window is too large, the training data will be too small. If the window is too small, also the training data will be larger, but the model will be trained with too many unnecessary frames.
Okay. Thank you for your presentation. So I would like to invite the last presenter of this semester, Cai Mo-Yue. So you may start when you are ready.
My name is from National Taiwan University, and my professor is Today I will present design of an high-voltage space vacuum detection system, integrating linear guideway and electromagnetic signals. Thank you for reading. Here is the outline of my presentation. I will start with introduction and related work. Then I will explain our contribution and the method, present the experimental results and the end conclusion. With the increasing use of smartphones, tablets, and computer screens, digital eye strain has become a common issue. Visual fatigue is not only related to eye discomfort, but may also affect the attention and texture performance. Therefore, developing an objective and repeatable method for fatigue assessment is important. Although visual fatigue is a common problem, it is still difficult to evaluate objectively and continuously in daily situations. Some existing methods may be affected by personal perception, equipment limitation, or environmental conditions. Therefore, this study aims to develop a more practical and repeatable fatigue detection method based on EOG scans. The objective of this study is to design a fatigue detection system by integrating an automated linear guideway and EOG signals. The linear guideway provides a stable near point of convergence test, while EOG signals are recorded to observe changes in eye movement and responses. In addition, CFF measurement is used as an objective reference for fatigue labeling. Previous studies have proposed several approaches of fatigue detection. Subjective questionnaires are easy to use, but they are not suitable for continuous monitoring. Vision-based methods such as optical eye tracking or camera-based analysis can capture eye behavior, but they are often affected by lighting conditions, facial occlusion, and privacy concerns. EEG-based methods provide useful neural information, but the setup is relatively complex and may reduce user comfort. EOG is a promising physiological signal for fatigue detection because it directly reflects eye movement activity. Since visual fatigue affects blink behavior, eye movement speed, and gaze availability, EOG can provide useful information for fatigue analysis. Compared with camera-based method, EOG is best affected by lighting condition. Compared with EEG, it requires fewer electrode and is more practical for variable or long-term application. The proposed system integrates hardware control, EOG signal recording, objective fatigue level, and deep learning-based classification. First, the automated linear guideway provides a repeatable near point of convergence test. During the test, horizontal EOG signals are recorded. Then CFF measurement is used as an objective reference to label the fatigue scans. Finally, the processed EOG signals are classified using the lightweight 1D resonant model. In traditional NPC testing, the visual target is usually moved manually. However, manual operation may introduce variation in movement speed and pace. To reduce this variation, this study designed an automated linear guideway. The visual target moves toward the participant at a constant speed, which provides more stable and repeatable visual simulation. The system also integrated Python and Arduino to synchronize the linear guideway movement with EOG recording. Before model training, the raw EOG signal needs to be processed. In this study, beam removal and the FIR filter are applied to reduce noise and correct baseline variation. Then this dose normalization is used to standardize the signal amplitude, making the data more consistent across
sliding window segmentation is used to divide the EOG signal into shorter segments. These segments are then used as input sample for the deep learning model. This slide shows the classification model used in this study. The input is a segment EOG signal, and the lightweight 1D resonate is used to classify it as a wave or vacuum. Because EOG is a one-dimensional time series signal, 1D convolution is effective for tracking temporal features. The model uses residual blocks to learn deep pattern, while group normalization improves training stability. Finally, the model outputs a vacuum probability for each segment. Segment level prediction are then combined using soft voting to determine the final vacuum state. This slide shows the change in RMS and EPR, which are energy-related EOG features. After vacuum induction, both RMS and EPR decrease. This means that the overall signal energy and the low frequency power ratio became lower in the post-test condition. Although individual responses were different, the overall trend showed that visual vacuum may reduce the strength and the stability of EOG responses. This slide presents the change in MPF and the MPF, which describe the frequency distribution of the EOG signal. After vacuum induction, both MPF and the MDF increased. This indicates that the EOG frequency distribution shifts toward a higher frequency range. This result suggests the visual vacuum not only change signal amplitude, but also affect the spectral characters of EOG signals. This slide shows that the change in quasi entropy and the spectral entropy. After vacuum induction, both features increased, indicating that the EOG signal became more complex. Overall, these results show that vacuum-related change can be observed in signal energy, frequency distribution, and the signal complexity. To evaluate both subject generalization, if one subject validation was used. In this study, data were collected from 30 participants. Each participant provided 10 pre-test samples and 10 post-test samples. So the final data set contained 600 EOG recordings in total. In each iteration, one participant was reserved for testing, while the remaining participants were used for training. For the final evaluation, a 5-push soft voting sample strategy was adopted. This approach combined the prediction probability from the next 5 training approach and determined the final output through sample voting. The example model achieved an accuracy of 0.8, an F1 score of 0.8, and an AUC of 0.7. This result suggests that the sample strategy provides more stable and reliable predictions. This slide shows the ROC curve and the AUC results of the proposed model. The ROC curve evaluates the model's ability to distinguish between a wave and a vacuum state under different decision thresholds. This result suggests that EOG signal contains useful information for distinguished vacuum states. This slide shows the confusion matrix of the final soft voting model. Most of the wave and the vacuum FAQ samples were collected classified. Both these errors may be related to the visual difference in EOG patterns or signal instability. In conclusions, this study developed an EOG-based FAQ detection system that integrates automated visual simulation, CFF measurement, and a 1D resonance model. The results show that the EOG features change after visual FAQ induction, indicating their ability to reflect FAQ-related responses. Furthermore, the proposed model achieved promising performance under LOSO validation. Overall, these findings suggest that EOG signals have strong potential for objective visual FAQ monitoring. These are the main references used to support this study. Thank you for listening.
Okay. Thank you for your presentation. I would like to open the floor for 2 questions. Any questions?
How was your experience participate first to say for when we tested EOG and the CFF data were collected. After 1 hour of digital device use, the same measurements were repeated at the poster test data. Why did you use local validation? EOG signals vary greatly between individuals. Also keeps one participant completely during training, so it can better evaluate the model's cross-subject analyzation ability.
Why do you use LG signal for picture detection?
I use EOG because it is portable and less affected by lighting conditions. Also, EOG can reflect eye influence related to breakthrough. In the future, it may be integrated with VR or wearable device for real-time breakthrough monitoring.
Thank you. Before I close the session, I would like to say thank you for cooperation throughout the whole semester. And then coming semester, will not be the lecture of this seminar. Then Professor Wang and Professor Xu will attend
老师有说的对，那我的意思说，老师有说要不知道的，没有。